Hello students, welcome to another lecture of Advanced Power Electronics. So today we are going to start a new topic, that is isolated switching DC power supplies. Having covered switching converters as well as resonant converters, we move on to this topic because it will use both those concepts. That is why I taught them before this. And these are the topics that are given in the syllabus as far as isolated switching DC power supplies is concerned. The topics are comparison between linear and switching power supply, specification of SMPS, different topologies, that is flyback, forward, push-pull, half and full bridge, control requirements and techniques, and practical SMPS design configuration. Okay, so today's lecture is an introductory lecture, a short one, just to get into the things a little bit. We'll follow with the details in the next classes. Now, regulated DC power supplies are required for a large number of analog as well as digital circuits. Now, these regulated DC power supplies must generally fulfill the following requirements. First of all, they should have a regulated output. That means the output must remain within a specified tolerance band, even if the input fluctuates within range or the load changes within some range. Okay. So even if the input changes or the load changes within a specified range, then the output must remain within a specified tolerance band. The second requirement is that isolation may be required to be provided between the input and the output. We say maybe, but generally it is a compulsion to provide isolation between the input side and the output side. And the third requirement is that there may be a need to provide multiple outputs of differing polarities as well as differing voltages. Of course, there are other common goals also, such as reducing the size of the supply, reducing the cost of the supply, and of course, improving their efficiency. Earlier, before switching DC power supplies were used, the linear DC power supplies were in use. Now, these linear power supplies, one of their major drawbacks was that they had a very poor efficiency. And that is why they have been superseded by switching DC power supplies. But still, before we study switching power supplies, it is worthwhile to see some linear power supplies. How did they work? How do they work? They are still working, they are still used. One of the most elementary or basic linear power supply is using a regulator IC. I don't know whether you have made it or not, but generally when we make hardware, we make a linear power supply using a regulator IC. 7805, all those ICs. So what those power supplies consisted of were, you had a AC input, typically 230 volt 50 hertz AC, and that AC was stepped down using a transformer. 230 by 18 volt transformer was used to step down the AC voltage. That transformer output was then rectified using a full wave diode rectifier. And then there was a capacitor to smoothen out the ripple in the rectifier output. And after that capacitor, you had a 7805 regulator IC. And that regulator IC maintains plus 5 volt for even if the input changes within a finite or specified range, or even if the output changes. This IC was again followed by another capacitive filter to further smoothen out the voltage, and so you had a perfect DC plus 5 volt available on the output. There is a family of these regulator ICs. If you want 12 volt, you go for 7812 instead of 7805, and so on. Okay, that is the most basic linear power supply, and we used to make it in the lab. The problem with those power supplies is they are very elementary, their efficiency is very poor, and generally their power handling capability is also very poor. So they are used only for low power applications. A more advanced linear power supply you can see on the screen. Here you have a single phase or three phase line input. If you have a single phase supply, of course, your capacitor size will increase. If you have a three phase supply, your capacitor size will be lower. Single phase supply, you use a single phase rectifier, and three phase supply, you use a three phase rectifier so that the ripple content is lower and a smaller capacitor can filter it out. Then you have a 60 Hertz transformer. In India, we use a 50 Hertz transformer. It is a low frequency transformer. And this transformer serves two purposes. The first is it provides isolation between the input and the output of the power supply. And the second purpose is it steps down the voltage to a value as required by the load, to a value suitable as required by the load. In the next slide, we will see how much the transformer should step down. But the transformer serves two purposes. It provides electrical isolation between the input side and the output side of the power supply, and it steps down the voltage to the range required. The output of the transformer is rectified using a diode rectifier. If the input is single phase, you have a single phase rectifier. If the input is three phase, you have a three phase rectifier. You can use a half wave rectifier, you can use a full wave rectifier, but generally you will go for a full wave rectifier. Now the output of the rectifier, it is going to be a pulsating DC that always has to be filtered using a filter capacitor. The aim is the output of the capacitor should be a perfect DC voltage. That will of course depend on what is the value of the capacitance. If you have infinite capacitance, you will get a perfect DC output. Let us for the time being assume that the capacitor voltage VD is a perfect DC. Then you have a transistor, and this transistor is not operating as a switch, it is operating in the linear range so that it behaves like a variable resistor, and the value of the resistance can be controlled using the base current. That is why it is a linear power supply, because you are operating the transformer in the linear range. If you operate the transformer as a switch, then it becomes a switching power supply. So this transistor, sorry, not transformer, transistor, this transistor is followed by the load. This is the output voltage. Now this output voltage is compared with the reference voltage, and the error signal is amplified and given to the base control, which controls the base current of the transistor. So the effect here is that the voltage drop across the transformer should be such that the output voltage should always be equal to the reference output voltage. If you apply KVL here, we get VD is equal to VCE plus V0, or VCE should be equal to VD minus V0. If your VD is fixed, you know the value of V0, so accordingly you change the value of VCE so that you get the desired output voltage. This is an example of a linear power supply. This is the capacitor voltage. You have a range here, minimum and maximum. So your transformer turns ratio should be such that your VD minimum should exceed V0 by a small margin. If it exceeds V0 by a large margin, your efficiency is going to go down a lot. But VD minimum has to be greater than V0, of course. VD minimum, this voltage has to be greater than the desired output voltage, of course. Because we are not going to increase the voltage here, there is only going to be a voltage drop. So what are the shortcomings of this linear power supply? Why do we need to study isolated switching DC power supplies? The shortcomings are, first of all, you need a low frequency transformer. Low frequency transformers have a bigger weight as compared to high frequency transformers. Second, the overall efficiency of a linear power supply is poor, 30 to 60%, because You are using the transistor in the linear range as a variable resistor. So basically you are dropping the voltage. You are dropping the voltage across the resistor. If this voltage is much greater than V0, you are dropping a much higher voltage across the resistor so that your efficiency goes on decreasing. That is why it is essential that this VD minimum value of this VD should be slightly greater than V0 only, not much greater than V0. But of course, it has to be greater than V0. But there are some advantages also. That is why they are still being used. First of all, the circuit is very simple. And second, they do not produce large EMI with other equipment. They are cost effective also. If your power rating is low. For low power rating, you will always go for a linear power supply. You will never go for a switching power supply. So I'll stop here, and in the next class, we'll go further. Thank you.